Hi and welcome. So now we're going to talk about matrices as linear transformations. So in the previous video, I talked about how we can consider a matrix as a matrix transformation or as a function. Now what we're going to do is consider a matrix transformation that usually looks like T of x equals AX, and we're going to talk about how this is actually a special type of function or transformation called a linear transformation. So there are lots of different types of linear transformations, and matrix transformations are just one example of them. So we say that a linear transformation is a special type of function, let's call it L, that preserves scalar multiplication and addition. So that phrase, preserves scalar multiplication and addition, means something really specific when we use it in a math context, so let me explain what it means. First, if we take L with an input of alpha times x, where alpha is a real number, we should be able to say that that's equal to alpha times the linear transformation of just the input x. So multiplying the input by that scalar value should be the same as just multiplying the output by that scalar value. We're defining linear transformations this way. This is just a special quality we want it to have. So this is the scalar multiplication, and we'd like it to be preserved, and that's what that phrase means mathematically. Then, to do our preserving of addition, we'd like to be able to take the function or the linear transformation L of x plus y, and this should be equal to L of x plus L of y for any two of our inputs x and y. So we should be able to take the linear transformation of the sum or the sum of the linear transformations and have those be equal. So these are just two special qualities we often care about when they're put together, and this is what we define as a linear transformation. So we're going to show that matrix transformations satisfy these two requirements, but I just want to note that this definition I've written here is a pretty simplified version of the concept of linear transformations. Linear transformations really involve vector spaces, which is a whole other concept that has lots of things going into it. So just know that the details with vector spaces are happening behind the scenes, and we're just going to do a little bit of an overview of how matrices work as linear transformations. Basically, I think it's important for you to have seen this before and to understand that a matrix is a linear transformation. So my claim, and what I'm going to prove to you sort of casually, is that a matrix transformation T that goes from Rn to Rm, and we have T of x equals A of x, this is a linear transformation. So to prove this, we need to show that the two qualities hold, that the transformation preserves scalar multiplication and addition. So we want to show that T of alpha x is equal to alpha times T of x, and we want to show that T of x plus y is equal to T of x plus T of y. So let's start with the first condition. So if we have T of alpha times x, what the function T is doing is that it's taking the matrix A and multiplying it by the input. So we have A times alpha x. So you could imagine we could write out our matrix A, we could write out our vector alpha x, and we could do the whole multiplication, and then at the end we'll be able to just take that scalar alpha out. So I like to think that we're just factoring that alpha out on the outside, so we have alpha times A times x. Then A times x is just our function T of x, so that's exactly what A of x is. And so we're getting our alpha times T of x, which is what we wanted. So showing this formally is a little complicated and involves writing out a lot of general abstract matrices, and so I don't really want to go through it here, but if you're in my class, I'll have additional notes that are provided that show you the whole proof if you want to see it. I think the next condition is a little easier to see. So if we have T of x plus y, we want to show that this is equal to T of x plus T of y. So if we start with T of x plus y, what T does is it takes the matrix A and it multiplies it by the input vector. So in this case, it's x plus y. Now, matrix multiplication is distributive, so what we can do is just do A times x plus A times y. So you might be a little skeptical of this. As I mentioned, you could write out the full matrix and go through the process and see how it works. A formal proof would do that. But I'm just showing you the basics here, And so we're getting a times x plus a times y, which each of those terms is really just what t does to x and t does to y. So we're getting the condition that we wanted. So let me show you some examples of linear transformations that aren't matrices. Well, specifically, I'm going to show you one example and one counterexample. Let's start with differentiation as a function. So if you've taken a calculus class, you've found a lot of derivatives. So taking the derivative, or differentiation, is something we could consider as a function. So we could say that what L of a function f of x is that it takes the derivative d dx of our function f of x. So I'm going to show that this is a linear transformation. So by taking the derivative of a function, we are doing a linear transformation. So first, let's work with that L of alpha f of x. So what we've defined L to do is to take the derivative of the input. So we're taking the derivative with respect to x of alpha times f of x. Well, the way derivative rules work is that we can factor out the alpha. That's just a constant in front of the thing that we're taking the derivative of. So this is really alpha times the derivative of f of x. Then that derivative of f of x we can just rewrite back in function terms, so we can rewrite it as L of f of x. And now we've shown the condition that we wanted. We can do something similar with L of f plus g. So let's say we have two functions added together and we're taking the transformation of them. Then what the function L does is it takes the derivative of the input. So we're taking the derivative with respect to x of f of x plus g of x. Well, the way derivative rules work is that we can split this up into the derivative of f plus the derivative of g. Then when we do this, each of these terms we can write back in function notation. So we can write the first term as L of f of x, and the second term as L of g of x. And we've shown the second condition. So differentiation as an operation has the two properties that we define as being a linear transformation. It preserves scalar multiplication and addition. So let me show you a counterexample for something that's not linear. So squaring, so let's say taking x squared, is not linear, which should kind of make sense intuitively because it's like a squaring function, which isn't linear, which would be like mx plus b, what we usually think of being linear. But let's make sure that it follows with our definition of linear transformation. So let's define L to take an input x and square it, so it will output x squared. Then if we try to take L of alpha x and see what happens, we're going to be taking that whole input and squaring it. Then we need to square each part, so we're getting alpha squared times x squared. But this isn't the same as if we did the alpha first and then multiplied by the transformation. So if we did alpha L of x, what L of x does is it squares the input, so we're getting alpha times x squared, and that alpha x squared is not the same as our alpha squared x squared. So these are not equal, and so this transformation, where it squares, does not preserve scalar multiplication. The second condition also fails. So let's say we have L of x plus y. So what our function does is it squares the whole input, so we're squaring x plus y. Now to properly do this squaring, we need to distribute all of the terms. So I'm getting x squared plus 2xy plus y squared. Now this isn't going to be the same as if we did the linear transformation separately. So if we did L of x plus L of y, we would get x squared plus y squared. And this x squared plus y squared is not equal to what we got the other direction. So there we go. This is the basics of linear transformations. As I mentioned, there's a lot going on behind the scenes with vector spaces, and so this is just the basics, and I think it's important to know that matrices work as a linear transformation. That's it for this one. Thanks so much for watching, and I will talk to you in the next one.